number 27 from chapter 6.
27?
Mm-hmm.
Yeah. So let me log into the computer here. Now, one of these two really does involve some fairly, I mean, I don't know if I would call them advanced things, but more advanced than what we've technically covered in the class. I mean, you could do it. So one of them, like finding what the distribution of the ratio of the two things is, that's a little bit tricky. So that's the one you're asking about, right? Where I have two exponential distributions.
Mm-hmm.
I want to know what the probability that x1 is less than x2 is, for instance. So let's maybe just concentrate on that one for now. The other one, will it involve, the other one would involve, in a second here. Last night when I was doing my lectures, my pen died. My little light pen died, so that was frustrating. Okay, I think you guys can see what's going on here. So I had x1 distributed as exponential with parameter lambda 1, and x2 was distributed as exponential with parameter lambda 2, right?
Mm-hmm.
And I want to know the probability that x1 is less than x2. That's one of the things I want to know. They asked for the probability that z, or the distribution of z equal to the ratio of those two things. We might be able to do that, but let's first do this computation right here. Okay, so what is the joint density of x1 and x2? Since these two things are independent, what's the joint density going to be?
So it's just whatever f of x1 is times the f of x2. Just those
right, it's
two
going to be the product of those two
together.
things, yes. F of capital X1 of X1, and then F of capital X2 of X2, which, by the way, is, what is the density of X1? Well, it's lambda, remember it's like lambda e to the minus lambda x, right?
Mm-hmm.
So this is going to be lambda 1, lambda 2, e to the minus, okay, it's going to be minus lambda 1 x1 minus lambda 2 x2. Okay. And look, I mean, it's going to start getting annoying having to use all these x1s and x2s. I'm probably just going to start writing this guy as just capital X and this guy as capital Y. Okay. So then we have f of xy is just lambda 1, lambda 2, e to the minus lambda 1x minus lambda 2y, okay? And then how would I compute the probability that x is less than y? What would I do? How would I do that? Let me just write it this way. It's going to be the double integral over the set where x is less than y, right? Whatever that is, yeah, of the density. And I'll put dA right here because we haven't decided whether we're going to go dx dy or dy dx. Okay. So, and incidentally, for the exponential distribution, what's true about x and y? Like, what values are we allowed to use for x and y? What's the smallest like x could be? Well, and still get a contribution. You know, still get a contribution from the density. Remember, this thing is technically, the density is only defined for x and y both being equal to or greater than 0. It's 0 everywhere else. Anytime that is not true, it's equal to 0. But this thing, right, is for x greater than or equal to 0, less than y, less than infinity. That is the region that we need to integrate over, okay? So why don't we just let one of the variables, let's say, you know, let's let x, well, actually, how about this? Let's let y go from 0 to infinity. Okay, so it's going to be dy. Okay, and then what about x? What's x going to go between? If y is just roaming freely between 0 and infinity, what is y going, or if y is roaming freely between 0 and infinity, what's x going to be roaming between? Potential spam, or what's going on here? Okay. All right. So what's x going to be roaming between? Zero and what?
Would it be y?
Yeah. Right.
Is that, so I'm confused. Why can x also be 0? Because I thought x had to be strictly less than 1. Oh, well, because exact values don't matter, right? Because we're
Right.
dealing with
Right. I mean,
continuous?
technically, I don't even have to put
Okay.
equal to 0. Does that make sense?
Right. Okay. Yeah. Yep.
Okay, f of x, y. So we've kind of set this thing up rightly. Okay, does this make sense? Because we're about to compute this, right?
Mhm.
So please ask questions at this point if something is unclear. Okay. Again, probabilities are computed like in terms of relationships, you know, between two random variables. You need the joint distribution, and then you simply integrate that thing over the region in question. And in this case, it's the case that x is less than y all the time. That's the region we want to integrate over. Okay. Okay, so let's do this. So we have the probability that x is less than y is equal to, look, I could pull out the lambda 1 and the lambda 2, correct? I'm going to pull that out in front of the integral. Okay, integral from 0 to infinity, integral from 0 to y, and then it was e to the minus, I'll write it like this, e to the minus lambda 1x. I'm gonna write it in two pieces, e to the minus lambda 2 y, and this was dx dy. And which of these two things can I pull out of the first integrand? The innermost integrand. Okay, look, I have this innermost integrand that I need to do. One of these is completely indifferent to the variable x. It's like a constant. So, so what can I do?
So you could pull out e to the negative lambda 2 times y.
Yeah. So I can pull that out of there. Okay. So this is equal to lambda 1, lambda 2. Integral from 0 to infinity. E to the minus lambda 2y. All right, so let's think about what an antiderivative is for e to the minus lambda 1x. What's an antiderivative for e to the minus lambda 1x?
Minus e to the negative lambda 1 x over lambda 1.
Yeah, minus 1 over lambda 1, e to the minus lambda 1x. But of course, what about this what about these lambda 1s? What happens? There's a lambda 1 out here.
Mm-hmm.
That like cancels with this one right here. You know what I'm saying?
Mm-hmm.
And of course, this thing needs to be integrated between 0 and y, dy. Okay, so what do we get? Well, lambda 2, integral from 0 to infinity, e to the minus lambda 2y. Okay. We already canceled the lambda 1s. Okay, it's going to be negative e to the minus lambda 1y, correct?
Mm-hmm.
Negative e to the minus lambda 1y minus negative, which is plus 1. So really this is going to be 1 minus e to the minus lambda 1y. And this is dy. Well, that's interesting. Okay. So at this point, you know, we could kind of break these things up and we'll see what happens here. Okay. Okay, so this is equal to lambda 2. Okay, what would the first integral be? It would be the integral from 0 to infinity. If I distributed that e to the minus, was it e to the minus lambda 2y that I was distributing through?
Mm-hmm.
Dy. And then it was minus, minus what? Minus lambda 2 integral from 0 to infinity, e to the minus, which is lambda 1 plus lambda 2. Why is that what that one would have been?
Mm-hmm.
I'm doing this from memory, but can't I just combine the powers on the exponent, on the exponential right there? Yeah. Does that make sense, Emma, so far?
Yep.
All right, now here's the thing. Let's work smart and not hard here. Hey, look at this. Isn't this just the density of the, isn't lambda 2 e to the minus lambda 2y? Isn't that just the density of y? Wasn't that just the density of y itself?
Mm-hmm.
So why is that pertinent? Well, what do you know that's going to integrate to if I go from 0 to infinity? If I mean, that's the entire range of y. What's that going to end up being?
1.
1. Okay. Yeah, that guy's just 1. Okay, so this is just going to be 1 minus. All right, so what is an antiderivative? What is an antiderivative for e to the minus lambda 1 plus lambda 2 y? What's an antiderivative for that? What say you?
Minus 1 over lambda 1 plus lambda 2 times e to the negative lambda 1 plus lambda 2 y.
Right. So let's change this minus to a plus because we get another minus kicked out, right?
Mhm.
It's going to be lambda 2 over lambda 1 plus lambda 2. And this is going to be e to the minus lambda 1 plus lambda 2 y evaluated between 0 and infinity. Okay. Lambda 1 and lambda 2 are positive, right? All exponential parameters are always positive. Okay. Right. I mean, you can think of it as the number of observations always, but I mean, of course, 1 over lambda 1, or 1 over lambda is going to be the mean of the exponential, and the mean is always going to be positive. Okay, so lambda 1 and lambda 2 are positive. So when I take y to infinity, there's a minus sign right here. And so what is this e to the, right? What is this e to the minus lambda 1 plus lambda 2 as y goes to infinity? What's that going to go to? What do you think?
Zero.
Yep. Okay, and then I go minus this thing evaluated at 0, but that just gives me 1 times that, that ratio of lambdas. So this is lambda 2 over lambda 1 plus lambda 2, okay? So I don't know, let's maybe, let's see here, what do I get? Maybe I could write this guy as lambda 1 plus lambda 2 over lambda 1 plus lambda 2. And then some stuff cancels and you just end up getting lambda 1 over lambda 1 plus lambda 2. Which is kind of interesting, isn't it? Yeah? I think that's pretty interesting. So the probability that x1 is smaller than, or that, that x is smaller than y. Remember, x was the exponential with parameter lambda 1, and y was the exponential with parameter lambda 2. We just determined that this is the probability that x is smaller than y. Okay. This is a probability that we're going to, I guess, observe the first observation corresponding to x happens before the first observation corresponding to y. So that's kind of interesting that ends up being the probability. Was there an answer to that one? Or no?
No, there's no answer in the back of the book for 27.
Okay. But that's too nice to not be correct, right? Has to be the right answer. Does that make sense, Emma?
Yeah.
I'm not too concerned about, I mean, look. Yeah, okay. Let's start working on the other one. So I just want you to at least see this. So they said, what's the distribution of z equal to x over y, where what was the deal with x? X was distributed as exponential with parameter lambda 1, and y was distributed as exponential with parameter lambda 2. Okay? Well, okay. Hmm. So
If you want your sheets washed, just remember to take those up real quick.
here's what we can do. We can say, what's the probability that z is less than, you know, some little z or something like that? Well, this would be the probability that x is less than some multiple, right? And by the way, you know, z would be just some number bigger than 0. That'd be the probability that x is less than some multiple of y. You see that? Yeah? Does that make sense so far? So look, I mean, we have the joint density for this thing. We just did the probability that x is less than y. That basically, let me just say that we just did basically little z equal to 1, didn't we? We just did the probability that x is less than y straight up. And now we're just saying, what's the probability that x is less than some positive multiple of y? Well, how would you pull that off, Emma? What do you think? What do you think about that? How would I set up the integrals here?
So then we're just going to do something very similar to what we did before, but just adding in a multiple of z. Is that the
Yeah,
plan?
that's right. So we're going to let x go between 0 and infinity again, correct?
Mhm.
And then
So
what?
then it would go from 0 to zy.
Yeah. That's right. And then it would be, you know, lambda 1, lambda 2, e to the minus lambda 1 x, e to the minus lambda 2 y. And this would be dx dy. Does that make sense?
Mhm.
And by the way, this thing over here, that's the CDF of capital Z, correct? So that would give me like the CDF of capital Z. So the CDF of capital Z, which is equal to x over y, is given by this integral. Okay? Is given by this integral. So how would I get the density? The density for capital Z, how would I get it from the CDF?
You just take the derivative.
Yeah. F capital Z of little z, that would just be the derivative. Okay. So that, I mean, is it clear how you would proceed to, I mean,
Mhm.
to do that integral in a way similar to what we just did, Emma, right?
Yeah. Mhm.
So that's interesting. Once you can get the CDF, you can get the density, and you basically have the distribution. I don't know. I don't know that it's going to be any kind of like typical distribution, like the gamma or something. I don't think that's going to be true at all. But you're going to at least be able to say what the density is. So that's good news for us. Okay. Oh man, I kind of want to. I kind of want to do that thing. All right, here we go. I'm gonna do it. Just can't let it go. All right, so let's see. capital F sub z of little z. We saw that this, so it was the integral from 0 to infinity. It was the integral from 0 to yz. Was that right?
Mhm.
Lambda 1, lambda 2, e to the minus lambda 1x, e to the minus lambda 2 y. And this was oops. This was dx, dy, okay? All right. So this is going to be the integral from 0 to infinity. As far as x is concerned, lambda 1 and that are going to be helpful, but the other two things, lambda 2 and the stuff involving the y, those are basically constants. So I could use lambda 1 to help me do the antiderivative of the first thing. Okay, so this is going to be lambda 2 e to the minus lambda 2y. Okay, and the antiderivative is going to be minus e to the minus lambda 1 x, evaluated between 0 and yz dy. Does that make sense? So this is going to be the integral from 0 to infinity, lambda 2 e to the minus lambda 2y times, well, let's see here. It's going to be negative e to the minus lambda 1 yz plus 1. So this is going to be 1 minus e to the minus lambda 1 yz. This is dy. Okay? Once again, okay, I could kind of distribute this thing through here. What's going to happen if I do that? Well, let's see. It's going to be the integral from 0 to infinity, lambda 2 e to the minus lambda 2y dy minus, okay, minus what? The integral from 0 to infinity of lambda 2. Wow, okay. So what am I going to have here? It's going to be e to the minus the quantity lambda 2 plus lambda 1 z all times y. Did I do that right? Does that look right to you? I think it's right. And hey, what about this first integral? What's the value of that? That's the exponential density, and I'm integrating it over its whole range. What's that going to be?
1.
1. So let's stare at this for a minute and make sure I didn't do some wild-eyed, thing that's just not even true. I think it's correct, though. Okay, for the second one, and we're going to be done here in just a second. So f sub z of little z is equal to 1 minus the integral from 0 to infinity. Okay, help me out here. E to the minus, was it lambda? Lambda. It was lambda 2 plus lambda 1z, was it not?
Mhm. Yeah.
Y, and then it was dy, right? All right. So let's see here. What is the antiderivative of this junk? So first of all, lambda 2, lambda 1, z, y, everything inside is positive. So, we don't have anything insane going on there, right? Everything in sight is positive up there. Their minus sign makes the overall power negative. But what is the antiderivative of this thing? 1 plus, I'm taking into account that minus sign out front, but it's going to be 1 plus what?
Lambda 2 over lambda 2 plus lambda 1 z e to the negative lambda 2 plus lambda 1 z y.
Okay, y goes to infinity, right? And so this is y equal to 0 to y going to infinity. Okay, that exponent goes to, right? So the exponential goes to 0. That's going to be minus that thing evaluated at y equal to 0. So this is going to be 1 minus lambda 2 over lambda 2 plus lambda 1 z. Wow. That's pretty cool. That's pretty cool. I don't recognize that. I don't recognize that that CDF off the top of my head. But there it is right there. So what is the density going to be? Now, I mean, don't forget z was equal to x over y, right? We got that. What is the density going to be? By the way, I could rewrite this as 1 minus lambda 2 times lambda 2 plus lambda 1z to the negative 1 power, yes? Okay, so look, if I want to take the derivative of this thing, what am I going to get? Oh man, the negative 1 comes down, right? The negative 1 is going to come down. And that power is going to become negative 2, and I'm going to multiply by the derivative of what's inside. Do you see it's going to be lambda 1, lambda 2 times lambda 2 plus lambda 1 z to the negative 2, okay? Which is just lambda 1, lambda 2 over lambda 2 plus lambda 1 z, this thing squared. And this is for z greater than 0. There is the density. You want any kind of probability involving that new random variable, x over y. There it is right there. You can just integrate that thing over the interval in question and you'll get it. That's amazing. And by the way, if you go up and you stare at this for a minute, oops, let me see. If you stare at this for a minute, does this jibe with what we got before? Like when z was equal to 1? Remember before we had z equaling 1? Is that what we got before?
Mm-hmm.
Yeah, we did. There it is, sitting right there. Yep. Amazing. I think that's pretty cool. Does that make sense, Emma?
Yeah.
I think I don't think there's anything left with that on that problem now, is there? Nope. That's it. And like I said, I don't necessarily recognize that thing. Oh man, sorry guys. I can't let this go. I want to make sure this thing integrates to 1 now. Sorry. Jeez. Okay. So This will just take a second, and it's good practice. So let's integrate this thing. I want to integrate it from 0 to infinity. It was lambda 1, lambda 2 over, what was it? Was it lambda 2 plus lambda 1 z quantity squared or something? Is that right? Okay, what's this thing going to integrate to? Well, the antiderivative, yeah, the antiderivative of this is going to be minus lambda 2 over, oh, of course, we already know what the antiderivative is. It's basically over here. You know what I'm saying? The antiderivative is essentially going to be this, but we don't care about this 1. This 1 doesn't really matter to us, okay? I mean, we just took the derivative of this thing, for crying out loud. We know what the antiderivative is, okay? Okay, so the antiderivative is going to be minus lambda 2 over lambda 2 plus lambda 1 z to the first power, evaluated between 0 and infinity. Well, if you let this thing go off to infinity, you get 0, okay? And so it's going to be minus negative, which is plus lambda 2 over lambda 2 plus that thing with z plugged in for 0, which is 1, which is good news for us, right? So it at least meets the requirements of a density. So there we go. It's always nice when all of those things work out for us. Okay. What other questions do you have? What else? Thanks for asking, Emma. That was fun. Hopefully that got you a little bit of practice on multiple dimensional integrals and thinking through some of that. That can be tricky. By the way, did you guys understand what I was objecting to? I mean, I was trying to make a really big deal about that. The problem about arriving, 10 minutes after something. Did you guys understand what I was objecting to, hopefully?
Yeah.
The lecture?
Yeah.
Did that make sense?
Mm-hmm.
Yeah.
You were actually doing that problem. I was like, seems like we would run into a problem at one point, like with this. And then you were like, so this doesn't actually work. And I was like, oh, okay.
Yeah, right. Well, did you notice that when I first did it, when I first started doing the integral, I said, I mean, if you go back and listen,
Mm-hmm.
I was going to just set it up and do it the way that I ended up doing it.
Mm-hmm.
But then I was like, no, I'm just going to go through it as if that wasn't the case,
Mm-hmm.
and then show later, because I think it would have been too confusing if I would have just jumped straight in and started doing all of the, oh, I have to break it up into 2 pieces or something. Okay, but hopefully that made sense. When I first started doing it, I said something like, well, we need to be, I said, well, you know what, I'm just going to go. We're going to do this. And then we went through, and then I showed you what the problem was. So hopefully that was helpful to see that. By the way, I went and computed the actual probability, and it was something like 11 over, oh, in fact, here, I'll show it to you. I have it right here. I think I have it right here. Yeah. Is it? Where is it? Oh, it's right here. This it right here? Yeah, this is it right here. This is exactly the probability we had in the lecture. Can you guys see this?
Mm-hmm.
You get 11 over 36, which, what was the probability we got doing it the wrong way? There was that little nipped corner that goes wrong, yes? Was it when we did it the wrong way?
1/3, I think.
Yeah, it was a third, which is just, and this number ends up being just slightly smaller than that. You know what I'm saying? And by the way, it is possible to just compute the volume of that thing too, but you would have to think carefully about that, okay? because you had a weird parallel, you would have like a weird parallelogram or trapezoidal base. You'd have to compute the area of that, which I guess that wouldn't be that hard. You just have to compute the area of that trapezoid and multiply by 1, basically. Okay? So yeah. All right. Anything else pressing on your minds? I think that's pretty cool. Oh, and I think I was careful to point out we needed to multiply that by 2. Didn't I say that right at the end?
Yeah. Mhm.
You could swap the roles of X and Y in there. Yeah, so you get 11 over 36, which is pretty cool. Okay. So there you go. Well, it's Friday. Hopefully you guys can get a little bit of relaxation over the weekend. Enjoy yourselves a little bit. Yeah. Do you feel like that this has been more work or what? I mean, like doing stuff in an online format, do you feel like it's more work or the same, or what's your feeling overall?
For me, it's a little bit harder.
Okay. Yeah. 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 You guys feel that? Do you other people feel the same way? Yeah. You guys are. You guys are being kind of quiet. That's all right though. Well, hang in there. Keep asking questions. Thanks for coming and asking good questions. I always like that. So keep on pressing on for sure. We'll stay in touch and support each other. All right. Have a good week.
Sounds good. Thank
Thanks,
you.
Dr. Hammett.
Yep. See ya.